Okay. So, we are working with logarithms. The logarithm of y with a base of b, this is how we write it. We write log base b of y equals x. So if you notice that log and y and x are all like the same size, and then the base of b is called a subscript, it's smaller and it's a little bit lower. Okay, so just make sure that when you write the b that it looks smaller. And this is the case, so log base b of y equals x, if and only if b to the exponent of x equals y. So we have the logarithmic form and we have the exponential form, and these two forms look different, but they actually mean the same thing. Okay. So this equation is the same as this equation, even though they look completely differently. All right. And the way that we're able to say those are the same is because logs and exponentials, so logs and exponentials are inverses of each other. Anyone remember what inverses means? Yeah. They're opposites, or what else?
I was going to say, if you multiply something, then you can divide it.
Yeah, so what you're meaning is like they undo each other. Yeah, so opposites of each other, or they undo each other. So an example is like multiply and divide. What's another example? Add and subtract. What's another example?
Square root.
Yeah, square root and exponent of 2, right? So we've had all these operations that we've worked with in the past that are inverses of each other. And now that we're in Math 3, we're actually learning a new one, which we haven't seen before, and that's exponentials versus logarithms. Those are two things that would undo each other, right? And we're not going to use them to undo each other just yet. That's going to be a little bit later in the unit, but later you're going to be able to see how we can use those operations to help us solve by undoing each other, okay? So a lot of students, since this is the first real time you guys have spent a lot of time with logs, a lot of students don't know how to say it out loud, so we want to make sure that we can do that. So this equation right here, if you said it out loud, you would say x equals log base b of y. That's how people actually say it out loud. So please don't say log little b y. Or don't say log by. So we can say it out loud, log base b of y. That's how you say it. All right? Or low b. Oh yeah. Even after I teach students how to say it, most of them still say log by. But it's log base b of y. Okay. So x is the logarithm. That's what I'm going to say x equals the log of something. So x is the logarithm. B is the base. And y is called the argument. And I'm going to say that honestly, the only one you really have to know is that b is the base. I did not even know that y was called the argument until I filled out these notes that I stole from another teacher, and I had to Google it because I didn't know what was supposed to go in that space. So b is the base is really the only thing that we need to care about. All right.
Did you not look that much into it?
No, and I looked this up a while ago when I stole the notes, so it's been some time. Okay, so a couple things to know. We've had restricted values in the past, so we learned about fractions, and fractions have a restricted value where you can't have 0 on the bottom, right? That's one thing that we've learned in math. If you try to divide by 0, your calculator says error, it doesn't like it. Another thing that we've learned is that you can't have a square root of a negative number. When you try to square root a negative number in your calculator, you get an error message, your calculator doesn't like it, that's a restricted number. We are learning some new restricted numbers now. So these are things that if you tried to type it in your calculator would not accept these. And one is to have a base of 1 in a logarithm, or to have a base of a negative in a logarithm. Those are two things that we have to pay attention to. And the reason that you can't have a base of 1 is because 1 to any exponent is 1. So 1 to the 7th is 1, 1 to the negative 4 is 1, 1 to the 1,000,000th is 1, 1 to the 0 is 1. All of those things are 1. And if we look back and we think about how these equations are written, if I was to try to say log with a base of 1 of 5 equals, there would be no way for me to find a number that would do that. Does that make sense? Because I can't have, this has to say base to some exponent equals that number. There's no way for me to have a number that would equal 5. That's not possible. No matter what I do, my answer, it's always going to have to be a 1 right there. It couldn't be anything else, right? So that's the problem there. Base, no negative bases, and that's because there would be multiple answers. Does someone have music playing? Right. There would be multiple answers. So, for instance, if I had log with a base of -1 of 1, and I wanted to see this number over here, if you compare it up here, base to an exponent is what the y value equals. So I'd be saying the base of -1 to the exponent of x equals this y value. There's too many different answers for me to say that this is a unique solution. It could be -1 to the 0 is +1. It could be -1 to the 2 is +1. It could be -1 to the 4 is +1. There's no unique answer for that. And so that's why we're not allowed to use negative bases, because you can't have an equation that doesn't have a unique answer like that. Right? It's not saying every single number is the answer. There just would be a lot of different answers that are possible. Okay? So the reason we don't have negative bases is because there would be multiple answers. And again, your calculator will not let you use these numbers. It won't let you plug in negatives. It won't let you plug in 1. Okay? The last one is that the argument, or the thing that we're taking the log of, has to be greater than 0. And that's because there is no way to get a negative answer by raising a number to an exponent. So if we think about, if I had 3 to the 1, what's 3 to the 1? 3. What's 3 to the 0? 1. Right. What's 3 to the -1? 1/3. What's 3 to the -4? 1/81. Yeah. So if you look at all these, it doesn't matter if my exponent is positive or if my exponent is negative, I always get a positive answer. And even if my exponent is 0, I'm still getting a positive answer. There's no way for me to get anything other than a positive answer if I take a base that's positive and raise it to an exponent, right? And so that's the reason that this number, this thing that we're taking the logarithm of, has to be a positive number that's greater than 0, because the way that you get y is you take a number and you raise it to an exponent, and there's no way to raise a number to an exponent and get a negative answer. Not possible. Okay, so these are things that for today, honestly, we don't really care a whole lot about, but later when we start to work with equations, we're going to care, because it's going to tell us what type of answers we can have. So that's a good thing to highlight. We're going to come back to it. It'll make more sense when we look at it in the future. Okay, so this next part is what we're primarily focused on today, and that's just converting between logarithmic form and exponential form. And a lot of teachers all over the place call this different things. Some teachers call it the Tootsie Roll. Some teachers call it the Cinnamon Roll. Some teachers call it the Scorpion. Some teachers call it the Cloud.
Yeah, we call it the Twixie Roll.
The Twixie Roll?
Yeah.
The Twixie Roll? Or the Tootsie Roll? Tootsie Roll? My 65-year-old math teacher from high school called it the circle thingy. So I think that was the best name. But this is the process that you go through to convert the form. You start by circling the base, because the base of the log becomes the base of the exponent. So that log had a base of 2. So now our exponent has a base of 2. And then we get the numbers by going around in a circle. So the exponent to the 2 is a 3. And then the answer is 8. And did that leave us with a true equation? Is it true 2 to the third equals 8? Yes, that's true. 2 to the third equals 8. 2 times 3 does not equal 8, but 2 to the third does equal 8, yeah. Okay, so let's skip number 2. We're just going to focus on these ones first. So the next one, the base becomes the base. So the base of the log becomes the base of the exponent. So 12 to the first power equals 12. True? Yep. And then if we do the last one, we have a base of 1/2. And anytime you have a base of a fraction, you have to put parentheses around it before you put the exponent on there. So 1/2 to the -5th equals 32.
That's correct.
That's correct. So let's go ahead and make sure that we can plug this in on our calculator. So I'm going to type 1/2 inside parentheses. And you can type it like that, or you can use the fraction button. It shouldn't matter. To the -5 does equal 32. So we know we got it right. Okay. So that's how you convert from a log into exponential form. Converting from exponential form back into a log is the exact same process. So again, we're going to circle the base, and the base of the exponent becomes the base of the log. So this exponent had a base of 4, so our log is going to have a base of 4. And we're going to do the Tootsie Roll, or the cinnamon roll, or the cloud, or the scorpion, or the circle thingy, whichever you prefer. So log base 4 of 1 equals 0. So this next one would be log with a base of 1/4. And notice whenever I write the base, I'm making it small. It's a subscript, so it's a small number that's lower. So log with a base of 1/4 of 4 equals -1. And then last, we have log with a base of 3 of 81 equals 4. All right, how do we feel about converting them? Easy? We're good? Okay. So go ahead and take that note page and flip it over. So now what we're doing is we're evaluating, and when you evaluate, you say what it equals. So we're going to write down what each of these expressions equal, and we're going to do that using our chart. So if you don't have your chart out, go ahead and get your chart from the other day with all your exponents and what everything equals. Okay, I don't know the answer right now, so I'm going to go ahead and put an X in here. And most of us probably can't look at a log problem and be like, oh yes, the answer to that is 17. And I know this because I've worked with logs my whole life. Most of us can't say that. So what we're going to do is we're going to convert this into exponential form because most of us are more comfortable with that form than a log form. So I'm going to start here. The base becomes the base. So 4 to the exponent of x equals 64. And now you should be able to look at your chart and figure out what that exponent should have been.
Oh my God.
It should have been a 3, right? So 4 to the 3 equals 64. Now, I cannot go and say, oh, my final answer is x equals 3 because I'm the one who put the x in the problem. The problem did not say solve for x and have x there originally. Yeah. So our final answer is going to be log base 4 of 64 equals 3. I evaluated it, and my answer was 3. Right? So I'm not writing x equals because I am the person who put the x in there, not the problem itself. The problem was not asking me to solve for x. Okay, let's do it again. So this one we're going to say equals x because we don't know, and we'll go ahead and convert it into the exponential form. So base of 2 becomes the base of the exponent. 2 to the x equals 1/16. And when we look at our chart, we can see that that should have been -4. So that means that log base of 2 of 1/16 equals -4. All right. Has anyone started number 9 yet?
Yeah.
Yeah, it gets weird, right? So if we look at number 9, we're going to say our base becomes the base, so 1/3, and I'm putting it in parentheses. So 1/3 to the exponent of x equals 27. And this just became a solve that exponential problem by changing the base. So we're going to look at our chart and we're going to see where 1/3 and 27 show up in the same column. The 3 column. So 1/3 is going to be rewritten as 3 to the -1. So I took the 1/3 and I wrote it as 3 to the -1. And 27 is going to get rewritten as 3 to the 3rd. And what happens to these two exponents? Yeah, they multiply or you distribute. So I've got 3 to the -1x equals 3 to the 3rd. And ditch those bases. So -1x equals 3.
X equals -3.
Yeah, so we could divide by -1 and then we get x equals -3. Should I box that and say x equals -3 is my answer? Yeah, so I got to write it as though I evaluated it from the beginning. So I'm going to say log with a base of 1/3 of 27 equals -3.
So basically, no matter what, we just rewrite the original problem, and then whatever we find for x, we do the equal. Okay.
Yeah. So, and the reason we're doing that is just because if this is the same as if they asked us evaluate 2 plus 7, and if I said evaluate 2 plus 7, you'd be like the answer is 9. You would just say equals 9. You'd be done. But here it's hard for us to do these in our head like that, and that's why we're saying it equals x and then solving for x, because it's a little bit more difficult to do it that way. Okay, so go ahead and keep working on these. I think a lot of these we can get on our own, but some of them are going to be a little bit of a struggle.
Like number 15.
Yeah, well, number 15 is actually, it looks weird, but number 15 is actually pretty okay.
And number
7 doesn't go into what?
Wait. What about, yeah, it's 0. 7 to the 0 is 1.
Oh, my brain doesn't work.
It's okay. That's the one that a lot of people forget about. So, what do you guys think the answer is for number 11? 1, yeah. 5 to the exponent of 1 is 5. So log base 5 of 5 equals 1.
number 12 is 1/2, right?
Excuse me, what?
This is move with fast food, so let's slow down.
Is number 12 one where you can look and get the answer super easily?
I know X is going to be a negative number.
It's not going to be a negative, but it's got to make it. It's going to be a fraction. Yeah.
1/2.
Uh-huh.
Oh my god.
So how do we solve for number 12?
Convert 36 into 6 squared, and then 6 becomes 6 to the first.
Okay. So basically what we did is we looked on the chart to see where 36 and 6 show up in the same column. And in the chart, if you look at that, that's the 6th column. So 36 can be rewritten as 6 squared. So this gives us 6 to the 2x equals 6 to the 1. And then what can we do from there? Cross out the 6's. You get 2x equals 1. Divide by 2, x equals 1/2. Should I box that? X equals 1/2?
It'd be log 36.
We're not doing this now.
So number 13 is a little tricky because it's off of your chart.
It's -7.
Okay, so Katie said it is -7. Can somebody else tell me how Katie knew it was -7?
When you get to the 7, that's what so you take the opposite.
Yeah.
I just looked down on the chart because the other ones is like
Yeah,
like
so
250 times.
if 2 to the positive 7th is 128, then 2 to the negative 7th would be the fraction version of that. Yeah. Good.
But then she went to boyfriend.
Okay, I'm going to
He didn't look out.
You are so
He knew her since she was
I told you
born.
that's that WPS right there. It's that WPS. There you go, cousin.
To the
Third.
to the 5th.
Oh no. Like, I'm so fifth grade.
Hey, why are you thinking that?
And I'm in there, that's what it is. Like, that's those are the same base. See, I know way too much about subscription.
No, I don't. We're nowhere near blood.
All right. Are we on 15?
Yeah.
Okay. How did we start 15?
No.
How do we think we should start 15?
8 equals 8 to the 4.
Yeah. So number 15, I know that it looks different, but you start it just like the other ones, right? So we've got 8 to the x equals 8 to the 4th. So what does x equal?
4.
It equals 4. Right? 8 to the 4th equals 8 to the 4th. Right? That's a true statement. So we're going to say log base 8 of 8 to the 4th equals 4. 8 to the 4th equals 8 to the 4th. If you put what? It's not x 8 to the 1 because that says 8 to the 4. Oh, 1x? Yeah, that's fine.
Decrease that because it's kind of hard for me to look at it. Like, could you make it into 2 to the 3rd and then and it would get the same answer?
Yeah, because you'd have 2 to the 3rd, so you'd have 3x equals 12.
And then divide by 3.
And then you divide by 3 to get x equals 12. Yep. All right. Yes. You're confused? So I started off by rewriting it. I knew my base of 8. Okay, guys, let's be quiet so we can explain it. So we had a base of 8, and that became the base. 8 to the x equals 8 to the 4. And then I noticed the bases were the same, right? So that means that x has to equal 4. The bases are the same, so the exponents must be the same. And then I knew that since x equals 4, that means that when I evaluated, the whole thing should equal 4. Okay? All right. A couple more things that should be on these notes. We have the common logarithm is log base 10. That's the common logarithm. And this is actually really similar. We've seen this sort of thing with square roots. So let's say we have like a third root has a 3 right there, a fourth root has a 4 right there, a fifth root has a 5 right there. What should a square root technically have? It should technically have a 2. Does anyone ever write the square root with a 2?
No.
Why not?
Because it's just implied.
It's implied. It's super common. The most common type of root is the square root. We would get super annoyed if we had to write the 2 every single time we did it, because it's the most common one, right? So we don't typically write that. So we've also seen this with exponents. If you think like x squared has an exponent of 2, that's saying it's x times x. X to the third has an exponent of 3, x times x times x. But a plain old x with an exponent of 1, do we typically write the 1 in there? No, because that would get annoying. It's the most common exponent. If you were to write the equation like 2 plus 5 minus 7, you'd have to say 2 to the 1 plus 5 to the 1 minus 7 to the 1. And that would get obnoxious over time, always writing that exponent of 1. So we've seen this before in math, where if it's the most common version of that, you drop the thing that would make it annoying to write. So log base 10 is the most common log, and so the simple notation is just to write log. Don't put the base of 10 because it's the most common one. So if you ever see just the word log, that means that there's a base of 10 that they just didn't write down because it's common. Does that make sense? So we do that in math sometimes because we're lazy. That's the only reason. Okay. The other log that is special is called the natural logarithm, and this is log with a base of e. So the letter E there. And there's a lot of history behind this. I believe the E is because of Euler. E-U-L-E-R is the guy's last name. German, maybe? Euler? I don't know.
What is the
It's an E. It's an E. And his simplified notation is ln for natural log. Log natural? I don't know. I think it's from Latin, maybe. Yeah, ln. It's not one n, it's ln. And it's not capitalized, it's always lowercase, ln. All right? So that's an L and an N next to each other. All right, so now we're going to use what we know about common logs and natural logs, and I'd maybe highlight that. This is something that a lot of students forget. So we're going to use this to help us do the last 3 on the page. So this one says log of 1,000, and since it just says the word log, what's the actual base supposed to be? 10. So log base 10 of 1,000 is what they were actually asking us to evaluate. I don't know what it equals, so I'm going to go ahead and say x. And then I'll put it in that exponential form that I'm more comfortable with so I can solve it. So the base becomes the base. So 10 to the x equals 1,000. Does anyone remember the trick to put here? How many zeros? Yeah, the answer has 3 zeros, so what should the exponent be? 3. So 10 to the third equals 1,000. And so now we can go back and we can say with the original problem, log of 1,000 equals 3. Or if you wanted to say log base 10 of 1,000 equals 3, you could put the base in there as well. I would not mark you down for putting that base back in. All right, for the next one, we need to have that base so that we can do the Tootsie Roll or the Cinnamon Roll or the Scorpion or the Circle Thingy or the Cloud, whatever you want to call it. So I'm going to take this and I'm going to say I know that ln is actually log with a base of e. So I'm going to write log base e, and that replaces my ln right there. And then I still have e to the 7th. And I'm going to say that this equals x because I don't know what it equals. So I took the ln and I replaced the ln with log base e. So now, let's go ahead and Tootsie Roll because it makes Daisha giggle every time. So e to the x equals e to the 7.
Wouldn't it just be e to the 7?
Yeah, so x must equal 7, right?
Oh, that's easy.
So on this one, we're going to say log base e of e to the 7 equals 7. Or if we're going to go back and write it in the notation of the original problem, then we can say that ln of e to the 7 equals 7. All right. On this last one, what should the base of the log be? 10. So we've got log base 10 of 1 over 10,000 equals x. And I don't know what this is, so I'm going to go ahead and rewrite it.
98. Would it be x equals -4?
So Nancy thinks that x equals -4. Does anyone know why she said negative?
Because it's a fraction.
Because it became a fraction, so that's good. We know our exponent has to be negative. And then why did she say 4? There's 4 zeros. So yep, that's exactly right. 10 to the -4 equals 1 over 10,000.
So it's log 1 over 1,000. Or 10,000.
Yep. So log of 1 over 10,000 equals -4. Or if you wanted to put that base of 10 in there as part of your answer, you could do that as well.